Welcome back from the break. Hope it was refreshing. Before going into the optimal control strategies, I will reflect a little bit on the workflow that mixes the things that you have been working with already. For example, a quite common workflow in engineering is that you use the dynamic programming tool to develop information and knowledge about how the optimal solution looks like, what is the optimal behavior of the controller. And when you have got a good understanding of what is the optimal behavior, then you go in and implement those in the heuristic control approaches to mimic the optimal behavior as much as you can. Now we will jump into the optimal control strategies, where we'll utilize analytical methods to extract what is the optimal behavior, and later you will implement that in hand-in assignment number 3. So we'll do a real-time controller with these optimal control based strategies. We have talked already a little bit about optimal control when we introduced the dynamic programming, but the main task we have here is to develop a control strategy that controls the state of charge Q over the cycle so that we get a charge sustaining strategy. And here you can see the fuel consumption that we're accumulating over the driving. So the mass of fuel ends up here. Depending on what we are doing with the state of charge, we can get higher or lower fuel economy. Hopefully we improve the fuel economy with the hybrid system. So when we formulate this in optimal control, we work with the optimal behavior. And the optimal behavior defines our performance index. So for example, in our case, we minimize the fuel consumption. So this is what we are working with mostly in this course, but we can also look at balancing fuel consumption versus emissions. For example, we can put penalties on emissions to balance these against the fuel economy. We can also include drivability criteria. This term here is called jerk. It's the derivative of the acceleration and squared. And then you can put a parameter here to penalize the control actions. However, in the course we are focused only on the fuel consumption. So we're minimizing the fuel consumption, and the driving cycle is specified, so we have no freedom to do anything. Our freedom is in the choice of how to use the electric energy that we have in the battery. The focus is also on hybrid vehicles that need to be charge sustaining. So we have a constraint on that the final charge should be the same as the initial charge. We will later look at plug-in hybrid electric vehicles where we will have a different constraint. That will be at the end of this lecture. But the interesting thing is that the plug-in hybrid electric vehicles can be treated similarly, where we have a discharge profile specified. So it's not that it's only one value, but we're specifying how the discharge should progress while we're driving. This constraint now can be included in different ways. Either we can have it as a hard constraint as we're having it here, or we can place a penalty factor. So for example, say that we would like to have this state of charge at the end equal to Q0. Then if we put a high penalty parameter here, we will squish these together. However, this penalizes high deviations more than small, and the deviation is also penalized independently of sign. Therefore, this equation is a little bit better to use. Here we penalize battery usage, and we favor energy storage for future use. So if we increase this term, it will reduce the cost. But we have that benefit that if we end up with a lower Q than Q0, that means that sometime in the future we need to do some recharging. And at the same time, if we have higher here, we will be able to go more all electric in the future. So this gives us an opportunity to work with the state of charge and plan for the state of charge. One more feature from the last one is that if we write it like this, we can actually rewrite it so that the weight times this Q becomes the same. It's just the integral of that one. And then we can rewrite the total cost function like this. And you see here we have the original cost function minus a variable times the Q. We have our original cost, and then we have a weighting factor times the constraint, and it was an equality constraint, so we can interpret this as a Lagrangian multiplier in the regular optimization framework, and that will come handy later. In the optimal control, we have the state equation. That's also included, where we have a description of how the state evolves over time. So we're considering a parallel hybrid with only one state, the state of charge, or equivalently Q of t is our state. So this is the problem that we were mainly working. We have our criterion function, then we have our differential equation, where we are looking at the state of charge and we are using that over the drive cycle to optimize the fuel economy. Then the control must be in the allowed region, for example. The fueling can never be negative, and we have a maximum fueling at every point. And the state of charge need to be in its allowed region. So now we have formulated an optimal control problem, and now we'll look at how can we solve this problem. And we'll turn to the theory with Pontryagin's maximum principle, and then come to ECMS, which is the equivalent consumption minimization strategy. If we look at all possible ways of solving these problems numerically, as you have understood from hand-in assignment number 2, it's more or less necessary to use computers and compute solutions numerically. And you have been working right now with the dynamic programming, so you have already covered that one, and we will now cover this part here where we're using methods that are called indirect methods, where we're using Pontryagins maximum principle to solve this problem. Then there are other methods that rely upon discretization, and that's the topic of entire courses and entire textbooks. So when I take a short commercial break and give reference to the course TSR03 on optimal control, where you can get a bigger toolbox for solving optimal control problems. So now we're working towards analytical solutions to this optimal control problem. We have a general problem formulation, as you have seen several times now. Then in optimal control theory, you define what's called the Hamiltonian. It's just to accept that this is defined, so we take this part, that's a continuous variable that is integrated, and we have this part that's also in the continuous world. This is just a single point, while these are continuous parts, and we put these continuous parts together with this Lagrangian multiplier. And this Lagrangian multiplier multiplies this constraint. So it's a dear child with many names. It's called Lagrange variable, it's called a joint state, it's called co-state, and most often denoted lambda of t, but in the book mu of t is also used just as a preparation for your future things that you can encounter. The Hamiltonian is repeated here, just to bring it along from the previous page. The necessary condition for optimality is we need to follow the dynamic of the system, that we need to fulfill the rules of the system, the Newton's second law, etc. Then, for optimality, the Lagrange multiplier needs to follow a differential equation that is specified like this. So it's a derivative with respect to the state of the Hamiltonian. And that will become useful later. Now we come to the most important point for solving this, and that's when we have the optimum state trajectory, we have the optimal control trajectory, we have the optimal co-state trajectory. Then, through Pontryagins minimum principle, they prove that this one will always be minimum. We can never find a control signal that improves and goes beyond this. So with this, we essentially change the problem for being a global problem so that we can look locally. So if we would know the lambda and the x, we can always compute u by selecting the u that minimizes the Hamiltonian. If we can write up an equation for the Hamiltonian, we can use that equation to get our control signal. And this is then the Pontryagins minimum or maximum principle, depending on if we're minimizing or maximizing the function. We're using minimization, so then we could say Pontryagins minimum principle, but it's the same for maximization problems. So if we set it up, we have our state that we can solve from this differential equation, and our lambdas can be solved from this equation. So we're letting these evolve, and we are continuously solving for u here. So we get our control signal u from these parts. Then the question, how can we find this variable? That is problem specific, so we need to go into the specifics of this problem to see how it's done. And when we now model a parallel hybrid electric vehicle in a driving cycle, as the cycle is given, the propulsive power demand is given from the powertrain, and we want to minimize the fuel energy. That's the integral of the fuel power that we have inserted into the engine. We have the freedom to use electrochemical energy from the battery, and this electrochemical energy is the voltage of the battery times the current that we're taking out of the battery, and that is our control signal. So the problem formulation with a charge sustaining strategy becomes like this. So we have the criterion function, where we would like to minimize the total energy of the fuel, which is the integral of the power flow of fuel. Then we have our derivative of the state of charge, which is the electrochemical power that we're taking, that comes from this guy, and power divided by u gives us the current. And as I defined it here, when we are taking energy and using it for propulsion, it's positive, so we get a current out of the SoC when we are extracting. But think of the sign convention that you're using in your own modeling. Then we have the charge sustaining part, and finally we have to make sure that the engine efficiency together with the transmission gives together with the electric machine and the power from the battery fulfills the propulsive demand. So this is the last algebraic constraint that you can utilize QSS thinking to bring into the equation so that you get the connection between the fuel and the electrochemical energy you're using. So this electrochemical energy is our U. So how do we solve this? Well, we set up the Hamiltonian. So we take this fuel power and then we take lambda times the different part of the differential equation. And then we use the necessary conditions for the adjoint state. So we just set up the equation, and this was the necessary condition that we needed to fulfill. And with the negative sign there and negative here, then this one does not depend on state of charge. It only depends on the control action and of where we are in the cycle. So we get the differential of this guy that pops out. Now I see that we have lost a lambda here. There should be a lambda also here. This is independent of SoC. This is also independent of SoC. This is the total charge that we can have in the battery. So this is the battery capacity down there. So the only thing that depends on the state of charge is the voltage. And this then ends up like this. So we have the differential with respect to SoC of the battery voltage. So let's look at that function now. Typical characteristics, we see that Q or state of charge has little or no influence on the voltage in the nominal operating region. So if we're operating here, we see no variations in the voltages. So that says that a good model for normal operation is that this derivative does not depend on the state of charge, which gives us that the time derivative of our co-state is 0, which finally means that our lambda becomes a constant. So we can replace the entire differential equation for it, and we know that, well, the differential equation is this, and we can replace everything with this constant lambda 0. This lambda 0 is now the thing that we need to search for. The problem is that we don't know what it is, and to get to that point we have to start the numerics. So up until now we have been working only with algebraic conditions and theoretical conditions, and now we have to work with the numerics. And the essential part of the numerics is to find that lambda 0, and we can do that pretty simply with the following algorithm. So you set up the model for the vehicle and engine with all the fuel flow, power electronics and electric machine, so that you model all the power flows, and then you set up all equations that you have and form the Hamiltonian. You make a guess on your lambda 0, and then you run a drive cycle simulation with that lambda 0, where you simulate the vehicle, and in each step you minimize the Hamiltonian to get your control signal, and you apply that control signal to the model. So then you're simulating with the optimal control signal given that lambda 0. If charge sustainability is fulfilled, then that lambda 0 is the optimum. If it's not, then you modify lambda 0 and you go to step 3. So then you have to figure out whether you should increase or decrease lambda 0 to get charge sustainability. One way of looking at this is that the driving cycle is mapped to a lambda 0. If we want to use it in normal driving, we don't know lambda 0 and we cannot iterate to find it. So how do we go about it then? If we have an incorrect lambda 0, the SoC will drift away from its nominal SoC reference value. And the solution is to start with an initial guess on lambda 0 and then look at SoC and update lambda 0 as we drive. We can, for example, use a PI controller that controls lambda so that the SoC that we're getting gets close to this SoC reference. This is given the fancy name adaptive ECMS, as it adapts lambda 0 to the current driving conditions of the vehicle. So a motivation for the name ECMS comes from that you look at the co-state variable that depends on the soft constraints, and we initially had this W as the weighting factor. We can have different efficiencies of the system for discharging and charging, and we introduced an equivalence factor by studying the battery and fuel power. So we introduce this S here, which is called the equivalence factor indices, where we have the fuel energy and we have the total energy of the battery. And then we can utilize this scaling factor here as a conversion factor between electrical energy and fuel energy. And that is what led to the word equivalent consumption minimization strategy. And there are ways of determining the equivalence factors from your system by analyzing the electrical energy or the fuel paths for different modes. So you have different cases. We can, from analysis of the powertrain, come up with these equivalence factors. You can also use simulation models to develop it and look at how the fuel consumption varies with different control inputs, whether you're doing charging or you're doing discharging, to see what does the extra fuel give you in terms of electrical energy. The application of ECMS in online implementation is then given by the following flowchart, where we are using the information about the equivalence factors, the lambda, and we get our S, and then we insert this S here, and we minimize the Hamiltonian. If we have the minimum, we use that optimal control input, and if not, then we update the information and we search. So this is searching for the optimum. In some cases you can in fact solve this minimization of the Hamiltonian analytically. There is also a telemetry ECMS where you insert map information. The telemetry is that you have information available from future driving. So coming to the final point where we will put these things together that were developed for a regular hybrid electric vehicle, we can see that it will be applicable also for plug-in hybrid electric vehicles. For plug-in hybrid electric vehicles, we start with a high state of charge and then we go down to a minimum point. So we have a window here that we are operating with the state of charging. We have charged at home and then we drive. And the main strategy that is utilized if there is no planning available is called charge deplete and then charge sustain. Charge depletion, charge sustain strategy, CDCS. So we go down here, we deplete the battery, and the reason for selecting this strategy is that statistical analysis of vehicle usage shows that most trips are very short. So then it's a good idea to use up all electricity as fast as possible, because the trip is most probably short. But if you have knowledge about future driving, then you can really improve the situation a little bit. And that's what's illustrated here in terms of the blended trajectory. We know that we're ending here, and we plan for ending with a state of charge here. If we would stop earlier, it would mean that we have not utilized all the electric energy. Some examples here: 5 commuter tracks, the same car going the same route, but there's a little bit of variation depending on the traffic situations. And you have the route presentation from the map data, gives this, and then there are different profiles. And then if you compute it, a SoC reference from some model where you want to have the minimum fuel consumption, you get the following track. And then if you compare control strategies that utilize this SoC reference, or if you use a charge depletion, charge sustain strategy, you have the green ones here. So if you start comparing them to each other, we have reference data, we have simplified model, and then we have dynamic programming. In dynamic programming, the cost to go function can, from control theory, be differentiated. You can get your co-state lambda from the cost to go calculation that you have done if you utilize dynamic programming to solve this problem. 5 different runs here have been run with the different control strategies, and the fuel consumption have been compared. This was done by Victor Larsson, Lars Johannesson Mård, and Bo Egart, where Victor Larsson is usually guest lecturer here for this course, but I don't know what will happen this year with this COVID situation. But we have here, the most important part here is the fuel economy that we're looking at, and the charge depletion, charge sustain strategy has the highest fuel consumption, and then if we use the dynamic programming cost to go, we get the lowest fuel consumption, and then with the different models we can get a significant improvement compared to the charge depletion, charge sustain, but not as much as the dynamic programming cost to go calculation. This is equivalence factor, and this is also an equivalence factor, but the equivalence factor has been extracted from the cost to go function. And you can see how much current we are taking out or putting into the battery. And the charge depletion charge sustain has higher C rate in average than the others. But the most important part here is that by having planning available, we can get access to 7 to 9% improvements in fuel economy compared to the simple charge depletion charge sustain strategy. One of the main messages from this lecture is that planning can improve the fuel economy, and this is something that you might get possibility to work with after you finish studying at all the manufacturers. But it's not only in the automotive industry, the same thing goes for train industry, and also the same thinking can be utilized for electricity. We have dynamic prices of electricity, and you would like to, for example, minimize the cost for charging your vehicle or minimize the cost of running your own home. If you think about having a power bank at home, a backup battery, the toolbox that you have received now is useful for many things like that. This summarizes the thing that you can utilize for feedback control of plug-in hybrid vehicles and also of regular parallel hybrid vehicles. And with that, I finish this lecture and see you in the Q&A session that starts at 12 o'clock today. Till then, bye!